Hello, welcome to SS330 Sustainable Manufacturing Systems. This is lecture 2, Facility Layout. Alright, so the topics that will be covered in this lecture include the 4 common layout formats, systematic layout planning, and also assembly line design. First, let's look at 4 typical layout types. Well, the first layout type is the worker centers. Sometimes we also call it job shop. So in this kind of a layout type, usually we group similar machines into one work areas. For example, in this area 1, I'm probably gonna put several machines, same or very similar machines together. Maybe these are the mill machines. And then in another area, I'm going to put another type of machine. For example, these are the drilling machines together. And another area, maybe these are the lathes together. So in this kind of setup, when we have a product to be made and the product requires several processes, then we'll go to the first process. And then after it's machine or after it's worked out, and maybe this machine, maybe this machine, maybe this machine, or this machine, which machine is available or capable of doing that process. And then the product will move to another process to go to the being processed another process, and then it'll move to another area and being worked out at another process. So in this case, those kind of job shop layouts, it requires the products or the operators or the material handlings to go through a lot of places, and it's a long traveling distance. But the benefit of job shop is that it provides a lot of flexibility, or it can make more variety of products because of we groups those kind of products or machines together. So this is the job shop or setup. Well, another type of the setup is the assembly line. So assembly line has been we have been discussing that in the last lecture. And assembly line usually it's a sequence of the processes, and usually assembly line is more fixed than work centers. So the work centers they can make variety of different models because machines have more flexibility. While in assembly line, all the setup and the machines are more fixed, and the models can make is very limited. A lot of times it's only one single product, or sometimes it can be very limited models. So this is assembly, but compared to work centers, it's more efficient, because the material flows goes to a very single direction, and the traveling distance will be really limited. So that's why it makes it more efficient in assembly line when it is making only very limited models. Well, another type of the layout is manufacturing cell layout, as cellular manufacturing. We kind of discussed that in the first lecture. In manufacturing cell, we gonna group several processes together. Maybe this is 1, 2, 3, and the parts will go through all these processes to make a composite part, right? And then after the cell 1, they're gonna probably move to the cell 2. Then we get another type of process, maybe 4, 5, 6, to make another composite part. So this is a manufacturing cell layout instead of assembly line. And the last kind of layout is a project layout. So project layout is usually used for bigger projects such as airplane, right, or ship that is really hard to move or transfer from process to another process. Well, in this case, we'll build all the processes around the project, right? We'll build all the process around the project, and then the final product will also be produced here in the same location. So this is a project-based layout. All right, next now let's look at what are the input and output of layout decision. So in order for us to make a layout decision or come out with a layout plan, what information do we need so we can take care of all the factors that are affecting the plan? Well, the first, we have to know what is the space availability of the space. For example, a lot of times the shop floor is in a rectangular shape, but sometimes we can probably get a shop floor as of a different shape. Well, in this case, you will have to think about with this kind of shape of space, how where do you want to have the entrance, where do you want to have your exit, as well as how do you want to plan out all the transportation and flows in a different shape. Well, another set of information we need to take care of is the space requirement of all different resources. For example, equipment, right? Labor and offices and all the other facilities and functions. Then after we get a chance to know those information, then you can think about how do you fit the available places. And next one is the product demand. So when we are planning out the layout, we have to know what is the quantity or the capacity that we are making this kind of designing this layout. Because if we have a lot of materials, then we have to think about how much space that is needed to store the material, and as well as the travel distance. So travel distance matters a lot because you do not want to, put two processes or two functions that is really far from each other if they have really close relations that have a lot of transportation between them. Right, so and travel, sometimes they can be human travel. Sometimes they can be the cars or AGVs. Then that's the actual cost actually for travel. Well, another set of requirement will be the process requirement. Then you still have to consider about the process flows. For example, you might want to group a certain type of processes. For example, if it is all metal work or metal cutting lathes, all these kind of processes, you probably want to put them together so that it can it make it as similar process to be together, so they have the same environmental or safety considerations. And so, for example, maybe you can put all the metal work here, and then maybe there's a pin line somewhere here, and then maybe the assembly line somewhere here, and then packaging and shipping. So this is the one layout plan because you want to group similar processes together. Well, another type of consideration you want to consider here is environmental safety and health. Environmental safety and health. So environmental safety and health policies are important because when you are making a design or the facility, then you really have to comply with OSHA standards. And for different kind of machines, especially in manufacturing setting, a lot of those machines actually have potential hazard materials or accidents that you have to prevent potential accidents. For example, a metal 3D printer. Usually, when we're talking about 3D printer, it's always polymer or plastics, but there's another type of 3D printing is used. We are 3D printing metals. Well, we are 3D printing metals. Usually, we are dealing with raw materials as metal powder. So those kind of powders are actually really tiny, and you can even breathe that into your lungs. Then that will cause really serious disease if you keep working on that for a long time. So in this case, the OSHA actually established the standards for taking care of the human safety and health when you are dealing with metal powders. And if you are designing a layout for a metal 3D printer, then you have to think about, okay, how what is the ventilation standards, and also what is the space, and what are the procedures that need to be taken care of at that space. So that's all the consideration you have to think about in order to come up with a layout design for your manufacturing processes or facilities. All right, next we want to talk about one method. It's called systematic layout planning. So this is the one popular method has been used in industry for facility layout. So basically the idea is to first find out what are the closest relations between the processes and the functions. Then we start to draw a certain diagram, and then when apply some of the space requirements, and then refine the drawings and to come up with a space relationship diagram. Then in the end, we're gonna apply some other considerations to get a final layout design. So the next, I'm going to use one example to show how this systematic layout planning, or SLP, is used in an example. So this is the one example. This is for a floor of a department store. You can see, there are different departments of department store. There's a credit department, toy department, one camera, and candy department. Okay, and then in order for us to find out a layout or come up with a layout plan, the first we want to know what are the relations between those departments. Do they have a really close relations? They have to travel to each other a lot, or it's totally not related at all? Then we use this kind of relationship chart to come up with that relations, to come up quantify that. All right, so in this case, the relationship chart is we're gonna name them as 1, 2, 3, 4, 5 for each of the departments, and also we have the 1, 2, 3, 4, 5 in the horizontal direction. So here we come up with a matrix, and we can give values. Right, we can give values to the relationship between two departments. For example, from 1 to 2, right? From 1 to 2, it's from the credit department to the toy department. Well, from credit department to toy department, we define it as 6. So the value as 6. Then we're going to think about what's 6 mean, right? In this case, usually we develop the code matrix for the relations between it is close or loose, or is the reason, or what kind of reason it is. So for code here, here it uses code as the reasons, and it uses the letters to describe the values. So I here means important, right? I here means important, and the numeral weight for this is 4, and 6 here means it's psychology reasons. So from credit to the toy department, it's more of a psychology reasons that it's and the importance will be 6. Well, from 1 to 3, we can see this. From 1 to 3, so credit department to the 1 department, and it's U. U means unimportant, which means that it's not not quite related, right? It doesn't really matter at all, and also it's just not available for any kind of code because it's not related. There's no reason for that. But from 1 to 4, you can see it defined as E. E means especially important, so it's more important from 1 to 4, from credit department to camera department, and the code for that, the reason for that is 4, which is a contact necessary. So credit department to the camera department needs some kind of contact reasons for that. And also here in this column we have the area for each of the department. It shows what is the area for those departments. So this is the way that we establish the relationship chart. So sometimes we use the kind of weights, the values, and the codes, while sometimes we simply give transportation distances or frequencies of those. It really depends on what really matters in your layout planning, right? So if you think the transportation cost is really matters, then probably put here the value of the cost. If you think the travel distances matters a lot, then you put the travel distances. So it can be flexible in defining what is the actual value in this matrix. All right, so after we come up with this relationship chart, then we'll start to draw an initial relationship diagram. You can see from this from here. So initial relationship diagram, it maps out the relations of different functions, right? Like 1, 2, 3, 4, 5. You can see from this there are actually some centers. You can easily tell because if it is really important, you can see 2 to 5 is closely related. Well, right? So in this case, you probably want to have to put 2 and 5 together, and the next one is 1 to 4. So 2 and 5 to be together, 1 and 4 to be together. Then from this kind of chart, you start to have an idea of what are the closest relations are and who should be next to each other. Right? So now we come out with an initial layout-based relationship diagram. So this way. But this kind of diagram doesn't really count the space because still have this kind of area requirement. So after we put the space into consideration, then we'll come out with our final design, which is like this, right? So because 2 has 400 square feet, while the 1 credit department only has 100 square feet, and 3 has 300 square feet. So now we come up with our final design. So this is the way how to use systematic layout planning in order to come up with the layout design by drawing the relationship chart of the processes or the facilities. All right, now let's use another example to describe this. This is more of an exercise. So example 2, so available space is 80 times 160. So this is the total available space, and each work center is 40 times 40. So it makes it a lot easier because it's very consistent on all the work centers that have the same dimension. And the transportation cost is $1 to move a load between adjacent work centers, and $1 extra for each work center in between. So what does it mean? So it means if if you are moving one item or transport from one station to another station, for example 1 to 3, then it's $1, right? From 3 to 5, it's $1. But if you want to move 1 to 6, then you can go this way, and this way. So in this case, it's $3. Right? So that's $3. So this is how you count the cost of the transportation. Well, because of this, let me So because of this, then we collect the data and then come up with a relationship chart or the relationship diagram. And here we can see this is the chart of the matrix. And from 1 to 2, it shows the flow between the work centers. So flow between work centers means it's a number of moves per period, or it can be a day, or it can be an hour, or it can be whatever time period. But this is the flow frequency, so number of moves. you can see some of them are really large. For example, 374 for 6 to 7, while some are really not related at all, no move at all. From 1 to 4 is it's no moves. So in this way, so remember, for each move it is $1, right? It is the $1. So from this we can it asks us to come up with the design that is the least cost for the transportation, right? Least cost for the transportation. So this is all the information, and you can see the activities for 1, 2, 3, 4, 7, 6, 7, 8. These are the shaping, sieving, plastic molding, and stamping, metal forming, sewing, small toy assembly, large toy assembly, painting, mechanism assembly. Another thing you want to take care of is there's a loading dock here. So this is a loading dock, which means that you probably want to have receiving and shipping close to the loading dock, right? Instead of putting shipping and receiving really far from it, then you have to move really long distance to come back to the shipping. All right, so this is the conditions that we have for this problem. Now let's look at how can we come up with a layout plan. Well, for this problem, so we can, because we already have this kind of number of moves and also this kind of the matrix or relationship diagram, then we can use this diagram to come up with an initial relationship diagram. So the initial relationship diagram, we can draw it here. Let's call it step 1. So how we're gonna start? So we're gonna start with the highest number of moves, right? So the highest number of moves is from 6 to 7 here, 374. Then we're gonna probably use 6 and 7 together. It's gonna 6 and 7. I'm going to use some of the lines to demonstrate the frequency of moves. And then we're going to find out the next highest moves, which is 200 here. That is from 1 to 6. Right? From 1 to 6. Then we can use 1. And then mark it as 200. The next will be 187. So 187. So that's between 5 and 8. Because we do not have this, probably going to put it in another line since 5 and 8. Okay, 187. And then now 187, right? So next one is 180. So this is the 180, and it is between 3 and 8, and also 5 and 7. So 3 and 8 and 5 and 7. So 5 and 7, it's 180. 3 and 8 is 180. Now let's look at what is 3 is also close to. 3 is also close to 6. So you probably want to put 3 somewhere here. And mark it as 180. And 3 and 6. 3 and 8, and also 5 and 7. Already marked here. 3 and 6 is 125. 125. And then 1 and 2 is 170. Oh, make sure mark it off. And then 1 to 2 is 175. Let's put 2 here. 175. All right, now we have marked off most of the high frequency of moves or the number of moves, then let's look at next highest one. It will be 103, which is 6 to 8 is 103, and 2 to 4 is 100. So 2 to 4, I would not have 4 here. Let's put 4 here. 100. Okay. So that's 3 to 7 is 99. 3 to 7 is 99. And also we have some other, at 90s, and you can keep continuing finish all of those. But from what we already have here so far, you can see that what are the close relations are, right, from this initial diagram. All right, so in order for us to reorganize the layout, we probably want to start with 6, right? 6, 7, and 1, because these are the places that really kind of at the center of the layout. So we're going to put 6 here, and 7 close to 6. 7 close to 6, and then because 7 is also close to 5, and 5 is close to 8, then we're going to put probably 5 here, and then 5 close to 8, we're going to put 8 here, okay? And 6 is close to 1, 1 close to 2, 6 to 1, 1 close to 2, and also 6 is close to 3, right? 6 close to 3, and 3 is close to 8 and 7, so we're going to put 3 here, and here we're going to put 4. All right, so this is the kind of initial layout we come up with this kind of design. So next I want to do is, of course, you can always, it is not necessarily the final design, but this is kind of design that already taken care of the relations. You can always think of if there are better layouts. But then how do we test if it is a better solution or not? Then you, based on this kind of new layout, what we want to do is we want to count what is the total cost, right? What is the total cost with this new layout? For example, from 1 to 2, it's $175. So sorry, 175 moves. Then the 1 to 2, because it is adjacent to each other, so which means only $1. So it's 175 times 1, right? And plus, so 1, 2, 3 is 50 moves. 1, 2, 3 is 50 moves. So 1, 2, 3 will be $3 times 50 moves, because from 1 to 3 it has to go to 6, 7, and 3. And then from 1 to 4, because there's 0, so it's always 0. And then 1 to 5 is 30. So 1 to 5, 1, 2, 3, so it's $3 times 30. And then 1 to 6 is, I think 6 is 200, right? 1 to 6 is 200 moves. So 1 to 6, because it's next to each other, it will be $1 times 200, and plus 1 to 7 is $2 times 20, and plus 1 to 3 is 1 to 8 is 1, 2, 3, 4, $4 times 25. So this equation calculates all the relations that relate to this part, and then you can keep calculating the rest of the matrix, and then until you add it up all together to find out the final cost, right? The final cost for this layout plan. If you have another layout plan and you want to test it if it's good or bad, then or compared to this kind of the layout planning, then you can use that plan and then calculate again and then see if it is to compare the cost numbers. All right, so basically this shows how you use systematic layout planning to come up with the layout plan by taking care of the relationship between the processes and functions. Next, I want to talk about assembly line design. So assembly line design basically it's more like the cycle time analysis that we want to come up with a certain assembly line that is more efficient with the lowest cycle time, because sometimes you can group some of the processes together or some of the workstation together. Sometimes we probably want to split the process in order to reduce the cycle time. All right, so the steps for assembly line design, well, the first step is to specify the sequential relations among tasks using the precedence diagram, because the first time we need to know what the processes are and what is processed after each other, right? So that kind of sequence will be the condition or the first step we need to find out in order to come out with the layout design. And the next is to determine the required workstation cycle time. Right, so we are designing this assembly line. First, we need to understand that what is the required cycle time we have to achieve. Because, for example, we have a certain requirement or demand of the products or from the market. Then we are planning out an assembly line that have to meet that requirement with a high cycle time or really low cycle time. So if it is a really low cycle time, then we have to figure out how do we design this line in order to reduce that, right? But sometimes it's not really that critical. Then you probably can lift the restriction a little bit in order to achieve some other functions. So the cycle time is important for us to determine or coming out with assembly line design as well. The next one is determining the theoretical minimum number of workstations required to satisfy the workstation cycle time. So here is we use work counting time in order to find out how many stations are needed within this kind of cycle time. And also, then we select primary rules, which tasks to be assigned to workstations, and a second rule to break ties, because there are several tasks, related to completing the products. Then you have to put tasks into different workstation to that. Then after we assign, it would be the time to assign the tasks into different workstations, and then lastly we calculate line balancing efficiencies to make sure that we have achieved a better efficiency in line balancing of the processes. Well, these are the steps or the sequence. Now let's use one example to demonstrate how it works in the real world example. I'll go through the example first. So these are the equations actually already there. All right, so this is an example. The Model J wagon is to be assembled on a conveyor belt. 500 wagons are required per day. You have the requirements. Then the production time per day is 420 minutes, and assembly steps and time for the wagon are given in the following tables. So find the balance that minimizes the number of workstations subject to cycle time and precedence constraints. Well, because our assembly line design, we'll first have to find out what is the precedence, right, of these processes. So we need to draw a precedence diagram. Well, in order to draw this precedence diagram, first of all, we need to find out what are the relations between the two, between each two processes. We have this table. So this table shows us the relations. For example, A, the task time is 45 seconds, and the description is position the real axle support and the hand fastener and the screws to nuts, and task that must proceed, which means it's nothing, so which means A is our first process, right? B cannot start without A, so A has to finish first, then so that's why A is precedence of the B, and then C, what are the before C is B, so A after B and C. From this we can tell who is after what, right? So with this diagram we can with this chart we can draw a precedence diagram. So how to draw it? When I start with A. I'm going to start with A, and make sure when you are drawing this precedence diagram, always mark or put the task time here, 45 seconds, right? 45 seconds. And then after A is B, right? So after A is B. And B's time is 11 seconds. And then after B is C. So C is 9 seconds. 9 seconds. Then when it comes to D, so when it comes to D here, you can see there's no process before that, which means D is actually a new start, maybe from another part, right? So D, right? D is 50 seconds. And then next will be the E. E, okay? And after E, the next one is, so we have E and then F, right? So F is after C. So we're going to put F after C. And F is 12 seconds. F after C. Okay. And then there's another next to the after C. It's G is also after C. So you put G here. G is after C. And G is 12 seconds as well. The next one is H. So H is after E. Then I'm going to put H after E. And E is 15 seconds, and the H is 12 seconds. And I is also after E. So this is I is also after E. And I is 12 seconds as well. I is 12 seconds. And then after I, the next one is J. So J is actually after F, G, H, I. So for the J here, J is after F, G, H, I. And J is 8 seconds. And the next one will be the K. K is after J. And K is 9 seconds. So basically this is a precedence diagram, and you can tell it's not really difficult. All you need to do is just follow this table from one another, and then to find out what are the relations between the processes. Okay. All right. So next, after we determine that which process is after next, and then we need to determine the workstation cycle time that what kind of cycle time is required in order to meet our customer's need, right? So assume this is a condition that we do not have a production line yet, right? So we do not have production line yet, and you are the designer and you are the manager that need to design processes, design workstations that to fit the cycle time. Well, in this case, maybe the first thing we're going to find out is what is the cycle time we need, right? So remember the condition we have here is that 500 wagons are required per day, right? Per day. And production time per day is 420 minutes, right? 420 minutes. Now, with this information, we can calculate the cycle time and using the how much production time per day divided by the output per day, right? So be the production time per day divided by output per day. So what is production time per day? It's 420 minutes, right? Divided by the number of outputs, which is 500 wagons. Well, then what we get is for producing each wagon, how much time is required, right? How much time is required? Then we'll give the minute per wagon. But if you want to make it into seconds, then we can times 60. So we can convert the unit from minute to seconds. So from here, we can calculate that it's 50.4 seconds per wagon. So this is ideal cycle time, right? This is cycle time. All right. So someone may ask, well, Dr. Zhang, you mentioned in the lecture 1 that when we are calculating cycle time, we have to use line efficiency or some other information, but why we do not have this in this equation? Well, keep in mind, because right now we do not have any production line yet. We do not know the line balancing efficiency, because this is what we want to find out, right? We want to design a production line that with highest line balancing efficiency, which is 1, right? So that's why we are not using those equations by basically using the most simple way to calculate the ideal cycle time, so which is 50.4, right? Because we already know what is the production time. Is a production time per day we have, okay? And it didn't really say this kind of production time includes the lunch break or not, but this is the time we have it here. So that's why we use 420 divided by 500. All right, so next we're gonna determine the theoretical minimum number of workstations required. So that actually is so theoretical number of workstations required will be basically the number of workstations equals to, remember that that equation is work counting time divided by what? Divided by longest service time times the line balancing efficiency, right? But because we do not know the line balancing efficiency yet, because we do not know the longest service times yet, right? Because the longest service time is really based on the workstation itself. It's based on the workstation itself, right? So that's why we do not know the specific information here. And in this case, how do we find out the minimum number of workstations? Well, here, because it says it's a theoretical minimum number of workstations, so which means we can actually use cycle time. Sorry, let me change this to black. To red. We can actually use the cycle time to find out what is the theoretical minimum number of workstations. So total work counting time, you can find it out from here. It's 195 task times 195 divided by the cycle time, which is 50.4, and equals to 3.87, which is close to 4 if we round it up, right? So which means that we will need minimum of 4 workstations in order to achieve this cycle time. But in terms of if it's really 4, maybe more, right? All right, so now we know we need at least four workstations. Our cycle time is 54.4. Now let's look at how do we assign tasks into different workstations. Okay, so in order for us to assign tasks into workstations, there are actually some rules to assign them. Because we also want to find out which one we want to put in first or the next. So the rules are including different rules. So one rule is called number of following tasks. Number of following tasks. What does it mean? It means we're gonna start with with the task that with highest number of following tasks. Look at here in this precedence diagram. So which one has the highest number of following tasks? You can see it's 1. It's A, right? Because after A it has B, C, F, G, J, K. And after D we have E, H, I, J, K. But after J there's only one task, which is K, right? So here we always start from the first process, or first process, which is A or D, right? But we don't know it is A first or D first. Then how do we do that? We can count how many number of following tasks after that. In this case, we can come up with a table. Come up with a table to show it. So I'm going to start with tasks. And then this will be number of following tasks, right? The table will be the A is actually how many? Is it 1, 2, 3, 4, 5, 6? 6 number of following tasks. Then D is 1, 2, 3, 4, 5. D is 5. So both B and D have 5 following tasks, right? And then you can see C and E. C and E has 3 number of following tasks, and then F, G, H, I has C and E, C 1, 2, 3, 4, 1, 2, 3. Actually, C and E has 4 following tasks, and GHI has 3 following tasks. See if it's 3. FGHI has 2 following tasks. 2 following tasks, and then J has 1 following tasks. Right? J has 1 following task. So this is the number of following tasks table. Based on this table, we'll start with A, and then B and D, and then C, E, and then F, G, H, I, and then J. Well, someone may ask, well, after A, because both B and D have the same number of following tasks, should I start with B or start with D? Well, in this case, sometimes we apply for another rule, which is longest service time. Longest service time. Then in this case, you can build another table with the longest service time. So you count how much time it takes from each process, and then build another table. So from this table, if you think it's B has the longest service time than D, then you're gonna start with B. If D has a longer service time than B, then you're gonna start with D. So basically, you have a rule 2, and also rule 1. This is rule 2, right? So if it is tied based on rule 1, then you want to apply rule 2. Okay. All right. Now our last task will be to assign tasks into workstations. We know that we need at least 4 workstations. I'll just put station 1, station 2, station 3, and station 4, and station 5 if we need it. But for now, we put them in there. All right, so we're gonna start with our first task. This is the table. So the table is setup is like this. This column, the first column, is the workstation numbers. It's a workstation number, 1, 2, 3, 4, 5, and the horizontal row is the first one is the task. So here you put what tasks actually put in each of the workstation, right? You put in the workstation, and then next one is the task time. So task time means how much time has been used in this workstation. Because what we want to do is think of if we want to apply assembly line, and remember this. All we need to do is to find out. This is TC1, TC2, TC3, and TC4, right? Which one has the highest cycle time, right? For example, TC3 has the highest cycle time. Then the whole production systems, right, cycle time will be TC3, right? So the longest service time, right? Longest service time. So in this case, what we're going to do is we're going to put different tasks into each of the workstations, because each task probably can be really short and really long. And if this is, say, this is a 50-second, and we don't just want to put one task in with only 9 seconds here, right? So we actually put more tasks in order to save the space and also save the efficiency, making it more balanced. So this is why we are assigning tasks into different workstations. Now we know we have station 1, 2, 3, 4, right? So now our job is to put tasks into these workstations. All right, now let's look at the first station. First station always start with rule 1, right? Our rule 1 is number following tasks. We know the A is our first task we want to assign, so we put A here. And task time, so we have to go back to the table to find out what is task time is 45. So A is 45. Now let's look at, okay, the 45 is the A's task time, and the first station's task time is supposed to be what? To be 50.4 and no more than 50.4, because if it is longer than 50.4, and the cycle time will be longer than 50.4, right? So we want to make sure that if for each of the workstation is always equal or less than 50.4. All right, now we have the A. Our next task need to be assigned is B. So if B is only, say, 5.4 or less than 5.4 seconds, then we can actually put B here. But let's look at what is the task time of B. Task time for B is actually 11. So which means if we put B here in the workstation 1, then the total workstation cycle time will be 56, which exceeds the 50.4. So in this case, we want to less than or equal to 50.4, right? So in this case, our workstation 1 will only have one task, right? Even though you think that, okay, maybe there are some other processes really less than 5.4. Let's see if there's any time that less than 5.4. Actually, there's no task is less than 5.4 seconds. So in this case, actually, we only have have A in there. Even though there is a task that is less than 5.4 seconds, we still cannot assign that here in the workstation 1. That's because we always want to follow this rule to be our guide to assign tasks, right? All right. So next one, we'll put B in the workstation 2. Oh, sorry. Next one, we'll look at B or D. It's not ready yet. Should it be or should it be D? Because B and D is tied according to rule 1, now let's look at B and D's task times. So B is 11 and D is 50, which means D has a longer task time than B. Well, in this case, I'll start with D. Right, start with D. So D has 50 seconds. Okay. We also want to make sure that we finish the rest of the tables. So remaining assignment times will be 5.4. Physical remaining tasks actually is no. We can say none. That is not available. No, not applied. Well, here 50, and then remaining as the assigned time will be 0.4 seconds, right? Also none here. So in this way, we can finish the rest of the table with start station 3. After D, we have to assign B, right? Because B is the next process close. We have to be assigned according to the rule 1. So B is 11 seconds, and then remaining assigned time is 39.4. All right. So we still have 39.4 seconds left in this workstation. Now we need to look at, okay, what other tasks can actually be assigned in this workstation 3? So by looking at what are the feasible remaining tasks. So after B and D, we have to look at C and E, right? Because C and E are tied according to rule 1, then we have to look at C and E's task times. So C has 9 seconds and E has 15 seconds. So in this case, we'll put E first, right? Because physical C and E, according to rule 1, it's both are okay. And according to rule 2, it's actually E. Then put E here, and E is 15 seconds. And after this, we have 24.4 seconds left, right? All right. 24.4 seconds left. What are the feasible remaining tasks? Now, after E, we have C left. C has a priority, right? The task with rule 1, of course, it's also C and E. It's not available, not applied. So then put a C here. And C's time is 9 seconds. So after 9 seconds, we still have 15.4 seconds. Okay? All right, for 15.4 seconds, let's see, do we still have feasible remaining tasks, right? So after CE, actually have FGHI. Now let's look at FGHI's times. So FGHI, all of them actually have the same task time, 12, 12, 12, 12. And what about rule 1? So rule 1, they are all the same, right? According to rule 1, they have all the same number of following tasks. So actually, these are feasible ones. So IFGHI are actually feasible tasks. And according to rule 1 is IFGHI. All of them are okay. And according to rule 2, they are also tied. Well, in this case, what should we do? Well, in this case means after we apply rule 1 or rule 2, it doesn't really matter, right? So we can arbitrarily choose one. Now, for example, we choose F. Then F will be 12 seconds, and here we only have 3.4 seconds left, right? And do we have some other feasible tasks? No, we don't have that. Then we finish assigning workstation 3. The next we'll have to put workstation assign workstation 4. Because F, G, H, I are all the same, and we already applied F, then we can start to assign G, H, I, right? It doesn't really matter if you want to put I first or H first or J or G first, but that's let's start with G, right? After G was 12 seconds, and then 38.4 seconds left. Then we have HI available according to rule 1, all HI, and then H 12 seconds, so it'll be 26.4, and then it'll be I. Then next will be, let's put I here, it's 12 seconds, then we have a 14.4 seconds left. So 14.4 after FGHI, then it's J. Now let's look at J. So J is 8 seconds. I'm gonna put J here, 8 seconds. So then we only have 6.4 seconds left. And do we have 6.4 second for K? K is actually 9 seconds. So we cannot put K in workstation 4. Then in this case, none is available. Right? So when 5 will be K. It's 9 seconds. And then the last station is 141.4 left. And then there's all the processes, all the tasks has been assigned. So this is the way how we complete this, assignment table, right? In order to come up with assembly line. So this is what we come up with. We come up with workstation 1 is A, workstation 2 is D, workstation 3 is B, E, C, F, right? And workstation 4 is G, H, I, J, and the last workstation is K. So this is how we design this assembly line in order to fulfill the requirement that the cycle time is equal or less than 50.4, right? All right, so this is how we completed this. Make sure you understand the procedure and understand the rationale to for each of the step and how we come out with this design eventually. Oh, there's another last question I'm going to ask us to calculate is the line balancing efficiency. Well, in order to calculate line balancing efficiency, we remember how do we calculate this? We're going to use all the processing times at each workstation and then divided by assuming that all the workstations have the same longest service time, right? So now let's look at all the workstations. Which one has the longest service time? The longest service time is actually the workstation 2, which is 50, right? Now let's assume all the 5 workstations all have 50 seconds. And then we add all the total workstation times together. So the first station is 45, second one is 50, third one is 47, fourth one is 44, and the last station is only 9. In this case, we can calculate 195 divided by 250, and we get 0.78 or 78% of the line balancing efficiency. So this is how we calculate this line balancing efficiency. All right, so that's all for today. So main takeaway is that you know what are the information required for facility layout, and then understand the method of systematic layout planning, and also know how to